Okay, so I will talk about a paper by um, H.P. Gum and A. Rossini from 1984. And the title is Ideals in Universal Algebra. Well, as some of you may know, it was planned originally that I'll give it in October 2022, but here we are. Um, it's best that people listening to this talk have some basic universal algebra knowledge. I'll give a little review here as well. You can watch my uh, preliminary talk I gave. So the idea of this paper is to study kind of the most general algebraic situation where you have the notion of ideals, and specifically this. Well, you have ideals or rings, and those are kind of substructures, well, not really subrings of the rings, but subsets of the underlying set of the rings, which form subgroups that you can quotient by. So essentially, they're kind of things that lie inside your algebraic structures that you can quotient by. Um, so if you have any questions, please interrupt. But then I'll get started with some review first. Let me just. Oh, am I not sharing my screen? Oh, oops. Thank you. So let me share my screen. It's okay. You just missed the first slide. You missed this. Uh, me from the University of Algebra is Anonymous. Um, so yeah, let me get to the review. Uh, just one slide, and I'll review the notion of varieties and congruences because they're kind of very fundamental to this paper. I mean, of course, they're just fundamental notions of universal algebra, so we're going to need them. Now, there's a definition of a variety. It's an equational class of algebraic structures. And now what this means is that, so here's an example, we take some language without relation symbols, and it's a first order language. What this means is that we have some operation symbols and some constant symbols, and every operation symbol has an arity, and we can interpret them as actual operations, so functions from a power of set to the set itself, and elements of the set. And whenever we have this language and we interpret it all in a set to have some example, this is called the structure of the language. Now we can take all the structures of a language which satisfy some axioms, so to say, which can be written as just universally quantified equations. So for example, we can take this example where we take a language which has a binary operation symbol and a constant symbol, and we take all the structures which have these two properties, just kind of random properties, and this is going to be a variety. So the second property is commutativity, and the first one is this one. Now, what's not a variety is if we take the same language and take all the structures of it, such that we have this property that for every x there's a multiplicative inverse, so to say. And the reason it's not a variety is because, well, first of all, this is not a axiom that's of our desired form, where it's a universally quantified equality, and it's further not equivalent to one either. So we cannot characterize structures where you can multiply and have a 1, such that every element has a right inverse by universally quantifying equalities. Now, this can be seen because, for example, we can take an example of such a structure, the positive rationals in the multiplication, and we can take a substructure, which is the positive integers in the multiplication, and the superstructure of the positive rationals will satisfy this, and the substructure will not. However, in any variety, you have that it's closed under substructures, products, and homomorphic images. So for more, you can, as said, go watch my preliminary talk, or you can find this in any universal algebra book. Now, the next notion will be very relevant. It's the notion of congruences. And congruences in algebraic structures are kind of the most natural thing to define quotients by. In general, at least in classical set theory, we take quotients by equivalence relations, and here we do this as well. However, for it to work well with the algebraic structure, we need to require that the equivalence relations are so-called congruences. And what this means is that they need to be substructures of the product. So an equivalence relation on a set is a subset of its square, the Cartesian, that's what I meant by the product, the Cartesian product of it with itself. And we need to require, so we can view this for an algebraic structure and algebraic structure itself, we need to require that the equivalence relation is a substructure, meaning that it's closed on the operations that we induce on this. And if we do this, this is precisely requiring that all the operations we have give us well-defined operations in the quotient set if we take the underlying standard quotient. So the idea of this talk will be of this paper is to ask in which varieties we have congruences parameterized by sort of natural substructures, not substructures, but again, subsets of underlying set with some properties of algebraic structures. And these substructures or these subsets will be known as ideals. So here's an example. Of course, everybody knows, well, everybody familiar with usual algebra knows about quotients and groups and rings, and whenever we have that, we quotient by some normal subgroup or by an ideal, and we have associated equivalence relations. These equivalence relations will be congruences. But here's an example that perhaps more unusual, and you might have never thought about. We can quotient monoids. And for that, we take an equivalence relation, say we take the monoid of natural numbers in the addition and 0. And we take this equivalence relation which identifies things which are free apart. Now multiple free apart. We quotient naturals, we get three equivalence classes. And indeed, we can check that it makes sense to add them. So kind of adding modulo 3, and this works in the monoid as well, even though it's not really a normal submonoid, whatever that would mean. It's just that we can take this quotient and we get another monoid. In this case, we get the same thing which we get with the integers. We get the cyclic group for the 3. So this is kind of how it generally works when you quotient algebraic structures. And well, the natural question is when can we do the sort of thing which we do in groups or rings, where we quotient by kind of sub things, ideals. And for that, we introduced the notion of ideal. So this is a notion which is due to one of the authors of the paper, Ussini, I think from the 70s. But before that, I'll give some errata to the previous talk, because I had two mistakes there. The first one is on slide 11, I gave incorrectly that it's inclusion reversing instead of preserving. And on slide 13, I forget to require that it's an equational class, in the sense that it's universally quantified with equalities there. Axioms, we assume. So yeah, I'm not the most qualified person to talk about these things. So if you ever spot mistakes or typos, just please let me know. You can also interrupt me. And so this is in the previous talk. But now, yeah, to notion of ideals, and throughout we'll have to work over some variety, which makes sense because we're considering algebraic structures. And crucially, in our variety, we suppose that the underlying language has a constant symbol 0. I mean, it can be some other symbol as well, like 1, but just we have some constant symbol that we pick out. And something that you might note in all of the examples one knows from classical algebra of groups and rings, you always have some sort of neutral element, which is crucial for defining our subsets we quotient by. So in general, we define this notion of ideal. And for that, we define the notion of ideal terms. But let me also put the notion of an ideal here. So say we have this variety v into 0 throughout. This will always be fixed in this talk. Now, the notion of an ideal term is the following. We take some term in our language, and let's say it contains some of the variables of y, which I write here as y arrow, y1 through ym. And this is an ideal term if whenever we substitute 0 for all of these y's, for all the yi's in y, and we interpret this term with the substitution in any algebraic structure from V, it's 0. Now here's an example. We can take rings, and we can take terms y1 plus y2 and x times y. And these are respectively ideal in y1 and y2 and y. The reason for that is if I substitute for y1 and y2 0, I get 0 in the first one, and if I substitute for y 0, I get 0 in the second one, no matter what x is in any ring. So this is kind of the notion of ideal, that ideal term that one has in general. And so an example of a non-ideal term is this one. We have x times y for groups. It's not ideal in y, well, no in x. It's easily seen if we take the symmetric group of the 3 as x1, 2. For y, we take our 0. In this case, well, there's only one constant symbol in the language of groups. It's 1, or I mean, like the trivial, the neutral element. So here it's interpreted to be the identity. We compose, we get 1, 2, which is not the identity, which is not 0. So this is not an ideal term. Now, in general, once we have these ideal terms, we can now define the notion of ideal, which will be the right notion to quotient by. And the definition is as follows. So we have some algebraic structure from V, and we regard a subset of its underlying set, and we call that ideal. Whenever given an ideal term in Y, say Pxy, and we substitute for Y some elements from our, so for all the Y's, we substitute some elements from our to be ideal from I, no matter what we pick for C, we're going to stay in I. So essentially what we're requiring is that we can replace in the ideal where the zeros would be elements from our ideal, and we'll stay in the ideal. So one can verify if we have rings, the ideals will be precisely two-sided ideals. And let me just go through the proof to kind of maybe elaborate this notion a little bit more. Now, I say precisely, so there's two inclusions going on here, so we have to split our proof into two parts. First part is to show that any ideal in our universal algebraic sense is a two-sided ideal. That's not difficult to do. We have that all of these terms are ideal in the respective yi's. So I mean, it's not difficult to see. We plug in we plug in 0 for y or y1, y2, and we get 0 everywhere, no matter what x is. Now, note the first term actually depends, is ideal in 0 variables. So such terms will be precisely the ones which are constantly 0. Any ideal will have to contain 0. And now we have all of these terms. Now, if we have an ideal in the sense of universal algebra, we have that no matter what we pick for x, if we plug in for y elements from this ideal, we're going to stay in the ideal. And if we read out what this means, we're saying that the ideal is close on the addition, that is close on the taking additive inverses, it contains 0, and it's close on the scaling from either side. This is precisely the definition of a two-sided ideal from ring theory. So we verified that every ideal in the sense of universal algebra is also an ideal in the sense of ring theory, a two-sided ideal. Now, the converse, I mean, to show that every two-sided ideal is an ideal in the sense of universal algebra, we can do this as follows. We suppose some two-sided ideal of a ring. And now the useful observation to make here is that ideal terms can be thought of, or just generally terms what concerns rings can be thought of as polynomials, coefficients in the integers. Anything we can do in the language of rings is add, multiply, take over 0 or 1, etc. And this is precisely describing taking polynomials with coefficients in the integers. Intuitively, the integers are the initial ring, so that follows. So suppose we have some ideal term. We can think of it as a polynomial p. Let's say it's ideal in y1 through ym. We can write p as all of the monomial summands which contain a factor of yi, some factor of yi, and all of the ones which don't. Now, because p is ideal, if we substitute zeros for the yi's, no matter what xi's are, we get 0. So in particular, if we do this on the right-hand side of p equals py plus q, we get that q is constantly 0. So in particular, it's just 0, but well, I'll just keep it around here, but actually we just get that p is py. In particular, it means p is some sum of monomials, and every monomial has a factor of yi inside of it. So if we substitute for all the yi's elements from I, all of the monomials will have a factor from the ideal, and if we, so they will be in the ideal itself. So if we sum all of these monomials, which are now in the ideal, we get something in the ideal. So in particular, any two-sided ideal is kind of preserved by these ideal terms. In particular, it's an ideal in the sense of universal algebra. So this finishes the proof. But also, one thing I want to note is that these terms we started off with to show the forward direction, 0, x, y, y, x, minus y, y1 plus y2, they are kind of so-called generating terms for our ideal terms. We can note that if we have ideal terms and we compose them, so we just take one ideal term and plug it into the variables of one of the other ideal terms, no matter which one, we'll remain with ideal terms. It's not difficult to verify. And these ideal terms, for the variety of rings, generate all ideal terms in the sense that if we compose them, we can get any ideal term. So, yes. So someone asked to ask a question. Well, what goes wrong is that we need to, first of all, we need to define. So okay, sorry. The question for the recording, somebody is asking why we cannot quotient by substructures instead of ideals. So what goes wrong is that we need to quotient by an equivalence relation, and in general, it's not even clear how to define the equivalence relation from a substructure. What one usually does, one takes kind of, well, in rings or in groups, one takes the unique congruence which identifies the substructure with the neutral element. But in general, there might not be a neutral element. And if there is, we still want to require that there's a congruence that we get, that some sort of congruence exists like this, and it's unique. And for that, we need this an ideal. So what goes wrong is that the equivalence relation, we can either not define it, so it's not clear how to quotient by it. So you can think of an example. Maybe we take just some magma. It has no neutral element. We just have multiplication. Maybe it's like all of the, let's say, torsion-less permutations of an infinite set. Well, maybe we have to make sure that we don't get the neutral element, but we take some just abstract magma. We take some submagma. It's not clear what to identify it with. Usually what we do when quotienting, we identify the thing we're quotienting by with 0 as said. But if we don't have a 0, it's not clear how to do that. But if we do have a 0, to make sure that the equivalence relation we get is the congruence, that the quotient becomes an algebraic structure itself, we need to precisely require that these ideal terms are preserved. Because preserving the ideal terms, if you spell it out, is precisely saying kind of that the quotient works out. So I hope that answers the question. Though it's important to note that in general, we can still not quotient by ideals. It's still not quite clear how to get the equivalence relation, that congruence. And this is exactly what some varieties will have as a property, that we can quotient by ideals, and this will be called ideal determinant varieties. We'll get that in a moment. For now, this is just what ideals are in rings. You can do a similar computation for groups, get the normal subgroups. Here it's interesting to note that conjugation, if I take the term xy, x, y, x inverse, I take this term in the language of groups. This is ideal in y, because if I apply in for y the neutral element, I get x1, x inverse, which is 1, no matter what x is. So in particular, we need to have normal subgroups. You can just repeat the argument in a sense. Maybe the converse direction will be a little bit more tricky, because we cannot think of them as just these sort of polynomials, but it's the same argument. Right, so let's move on and try to relate these ideals to congruences, because again, the thing that one naturally quotients by are congruences. So if you want to quotient by ideals, we need to kind of relate them. And this is what this remark is doing. It relates to every congruence and ideal. Namely, if you have some congruence in an algebraic structure, again, we have this variety which contains 0 in its language. We can take the equivalence class of 0 on the congruence. And it's not difficult to check this is an ideal, so let's check. Suppose we have some ideal term in y, and we have some things from our equivalence class from 0 and the congruence to substitute for the yi's. And suppose we also have some x arbitrary to substitute for the rest. Now we want to check that once we apply px to these si's, we stay in the equivalence class of 0, making sure that's an ideal. So what we have, because theta is a congruence, is that if I apply px to s1 for sn and px to all the zeros, it'll still be equivalent under theta. Now, the reason this holds is precisely because theta is a substructure of our structure squared. If you write it out, just carefully think about what it means to be a substructure of our, the theta is an equivalence relation which is a substructure. We get precisely that if we have some similar terms, like we have, say, x1 similar to x1, x2 similar to x2, etc., xn similar to xn, and then s1 similar to 0, s2 similar to 0, etc., sn similar to 0. These are all in our theta. They're all similar. We apply some operation. Because theta is a substructure, we stay inside. So we apply this term p. And because it's a substructure, if we apply p to some elements within it, we stay inside the substructure. So we get that this holds. If you're unsure about this, you can just kind of carefully write out what it means to be a substructure of the square. And maybe if it's unclear what the structure on the square is, we just take operations component-wise. You can also think about category theoretically, it's a direct product, one of the possible isomorphism representatives. So we get this, we get that px, s1 for sn, is theta equivalent to px zeros. But px zeros is just 0, because p is an ideal term. So we get px s1 for sn is theta equivalent to 0. But this is exactly saying that s is in the equivalence class of 0. That pxs is in the equivalence class of 0, as was to be shown. So we see that applying ideal terms to equivalent classes of 0 for congruence stays within the equivalent class of 0 for the congruence. Particularly, we get ideals. So this leads to the definition of so-called zero regularity. And this is precisely just requiring that this is injective. So on the next slide, I'll give some more kind of injective, surjective, bijective terminology. But one can think about when it is the case that different congruences give different ideals. So congruences are characterized by the equivalence less than 0. Actually, sorry, not the next slide. I think the slide after the next one. So here's an example, just to kind of illuminate zero regularity. If you take V as the variety of commutative magmas with the neutral elements, so 0 is going to be the neutral element. We have one binary operation symbol and constant symbol 0. We can take this magma, 0, 1, 2, and then as our binary operation, we take the maximum of two elements, and our neutral element is 0. If you take the maximum of 0 with something, if that something is greater or equal to 0, you get that something. Just the case here with 0, 1, 2. We have these two congruences. The diagonal, which is kind of the trivial equivalence relation, it identifies everything with itself, nothing else. And we can also take this theta, which also identifies 1 and 2. One can check these are indeed congruences. Now, evidently, they have the same equivalence class at 0, but they don't equal, so V is not zero regular. Congruences are not characterized by their equivalence class at 0. And this is kind of important for us to think about if we want to quotient by ideals, because ideally, what we want to kind of, from an ideal, think of it as the equivalence class of 0, and go back to this congruence. But we cannot do this if there are multiple congruences to go back to. It wouldn't be clear which one to quotient by. So we need to require zero regularity in order to quotient by ideals. And so here's an example. In this variety, we cannot do that. So it's a natural question when variety is zero regular. And there is a characterization by Fichtner. It's not from this paper, but it's related to this paper, which characterizes zero regularity. And this is the sort of Malchev condition, which are these kinds of conditions which characterize properties of a variety by the existence of certain terms. So we have that V is zero regular exactly when they exist some terms, d0 through dn, such that they kind of recognize, so they're binary terms, they take two inputs. X and Y here are just variables, they're not sets of variables or anything like that, list of variables. These terms, they take two variables, so upon interpretation, two elements of our structure, and they're equal to 0 precisely when the two inputs are equal. So we can kind of recognize equality. And it makes sense that intuitively this would tell us that the congruence is characterized by its equivalence class at 0, because we can recognize equality by looking at 0 with these terms. So some examples, we can immediately see that the variety of rings is zero regular, which we would expect, because, well, we can quotient in rings by the usual ideals. So something I wish to be able to talk about, but I couldn't find an example, neither in the literature nor by thinking about it. Maybe if I thought about it longer, I would have found one, is the existence of a zero regular variety where we cannot pick just one term dxy, we need to pick multiple ones. All the examples one sees in this paper and in other papers that we've been able to find only take one term di, d0, and that suffices. So I've not seen an example with multiple terms, so if anybody comes up with one or finds it in the literature, I'd be very interested. And so that's that. Yes. So now here, yeah, this kind of injectivity, surjectivity characterization, which I think makes it maybe a little more intuitive. So for any algebraic structure A from our variety, let's say we have the set of ideals I of A and the set of congruences C of A. We want to kind of put them in bijective correspondence. This is our ultimate goal. Above, we have described a map from C to I. For every congruence, we get an ideal. We think the equivalence class at 0. And now, zero regularity is precisely requiring F to be injective. Now, we want bijectivity, and someone can alternatively add surjectivity and bijectivity. Surjectivity gives the notion which is called having normal ideals. So the image of the map F is called the set of normals of A. And so if all ideals are normals, one says that A has normal ideals. And together we say that A is ideal determined. And these are really the varieties that we care about. Also characterized in this paper by also Malchev conditions. I'll get that in a moment. Whenever we have an ideal determined variety, any ideal can be uniquely thought of as a congruence, and vice versa. Well, the other direction is always clear. We can think of a congruence as an ideal by taking the equivalence class at 0. But this means that we can quotient by ideals. This is exactly the sort of varieties that we wish to study or characterize, and they're characterized by some Malchev conditions, again, by these terms. We'll get that in a moment, I said. So yes. So also another question I would have very much liked to answer, I mean, give an example, but wasn't able to find neither in the literature nor by thinking about it, is the existence of a zero regular variety which is not ideal determined. So that we can think of all the ideals as certain congruences, but not all the congruences. Because ideal determinedness says not only that you can quotient by ideals, but also that all the congruences are precisely can be thought of as ideals. There's nothing else that quotient besides ideals. So I wasn't able to find an example. Again, if somebody knows an example, please let me know. So here's the key theorem of this paper, which characterizes ideal determinateness. So you can see it's very simple. We just have a binary term, but that's because we've already assumed zero regularity. So this is what we need to add to have surjectivity of f. So suppose we have a zero regular variety. We can also describe this by sort of Malchev terms condition, Malchev condition, by having these di's. Now, it is ideally determined precisely when there exists a term s, a binary term s, with these two properties. Very simple. We have that it's kind of nilpotent in the sense that if we plug in the same element twice, we get 0. And we also have that if you plug in 0 into one of the components and x into the other, we get x. Well, just one of the components, just say s0, x is x. X0 does not have to be x, but it doesn't matter. We can just switch around the inputs to get the condition as x0 is x to have different characterization, but just one of them, we have this. So this is a full characterization of when varieties have congruences correspond bijectively to ideals, so we can quotient by one or the other. And kind of, this is a very, perhaps intuitively satisfying way of viewing things with these Malchev conditions, because intuitively we are saying exactly what sort of kind of things we have to be able to do in the algebraic structure. Like usually, maybe in rings you can add and multiply, or in groups you can just conjugate and multiply, things like that. When we give these sort of Malchev conditions, we say precisely what we need to do in order to have these properties to be able to quotient by ideals. So in order to quotient by ideals and nothing but ideals, we need to have one that we can recognize things. So we have some operations which recognize when things are equal by looking whether it's equal to 0. And we have this other operation which is kind of nilpotent like this, and we have this property. This is exactly what one needs in order to have quotients be ideals, or rather, congruences be ideals. So intuitively, one can kind of think of that as requiring there to be subtraction of sorts. So one can quotient by ideals precisely when we can subtract, more or less. So I will not go into the technical details of the proof. It's a straightforward proof, but it's a little bit technical. Generally, this talk kind of tried to make it more accessible, especially because the audience is not many US algebraic. Kind of just give the feel of what one is doing and the general notions. But I will give a sketch of the proof. Here's the sketch. Again, this is an characterization. So there are two implications. The first implication is done by this general trick how one establishes Malchev conditions. That suppose we have some ideal determined variety. We want to construct this term. And the way one can actually construct a term from just looking at these general conditions is by looking at three algebraic structures in our variety. So something I've not covered neither in the preliminary talk nor here is that one can always in a variety take three algebraic structures. One can characterize it by the usual universal property and prove it exists by kind of a usual construction. And once we have this free algebraic structure in V on two elements, because we have a binary term, one can look at some congruences in it, and then using a famous lemma of Malchev, you can find this reference, constructs this term S. Now, the other direction, it's perhaps a little bit more technical. One can use a certain characterization of congruence classes, congruence equivalence classes at 0, and then argue about this characterization. I'm not going to go into that. It's a little bit more technical. You can find it in the citation of the paper, paper by Malchev. So it's in Russian. I'm not sure if there's a translation. Okay, so this is kind of the ultimate result of this paper. We have characterized, well, I guess Gum and Racine have characterized when ideals are precisely the things one can quotient by. It's when you have these terms di and s. So here's just kind of a list of examples which algebraic structures are ideal determined. So I've always put a variety, what the ideals are, then these terms di and s, proving that it works, and then generating ideal terms. For loops, you can see there's dot dot dot, and for Boolean algebras, there's also dot 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 in the di and s terms, just because I couldn't fit it in the table. So we have everything we would expect. We have R modules, rings, groups. Now loops are kind of a generalization of groups with drop associativity, and Boolean algebra as well. It's kind of nice. There we also talk about ideals as kind of these maybe you come across ideals in set theory. You can interpret these ideals in set theory when we look at the power set as a Boolean algebra, precisely as the ideals in algebraic structures via this. So we have all of these terms and the generating ideal terms. Maybe it's just a good kind of list of examples to keep in mind. We can also, instead of ring, take R algebras as well, just as instead of R modules, could have take abelian groups. It all works out. So some examples which are not zero regular, precisely when we do not have subtractions of sorts. So you can see in all of these examples that you can kind of go backwards. We can get to the neutral element from over elements by subtracting or negating or dividing, something like that. But if you take monoids or rigs, so rings without negatives, so bounded lattices, we cannot go back, and they're not zero regular. We cannot quotient by ideals. In monoids, it does not suffice to consider ideals to know what to quotient by. Indeed, it's not even clear how to quotient by a single ideal. An ideal might correspond to multiple congruences. So quotients in monoids cannot be characterized in this nice way, but in these other varieties they can. Okay, so for the last part of my talk and the second part of the paper, I will briefly go what's known as commutator theory. Just a very, maybe not even go over it, but just mention its existence, kind of talk about what one requires in order to talk about it. Because in the second part of this paper, it's considered how one can relate the notion of ideal to the notion of a commutator. So commutators, we know them from group theory and ring theory. Maybe if one works with commutative rings, one doesn't see commutators usually, but one can still define x, y minus y, x in a non-commutative ring and have something non-trivial to study. And this is also something which can be phrased universal algebraically. More or less all algebraic notions can be phrased universal algebraically. And it can be related, and it works specifically well in what's known as congruence modular varieties. So I want to talk about what congruence modular varieties are. It's not directly related in a sense to what one is doing, because I'm not going to illustrate why one needs congruence modularity, but I kind of want to show you what one needs to check in order to know that we can use commutators. And for that, we need to talk about some lattice theory. So let me just introduce some basic lattice theory. Now, lattices, it's not to be confused with lattices as discrete subgroups of Rn. They are these order theoretic algebraic structures, which can be characterized as follows. So lattice, we can think of some set together with two binary operations, kind of this upside and down, this or and this and, which usually are read as join and meet, like union and intersection, or supremum and infimum. This reason why it's like that. And these binary operations need to be commutative, associative, and important, and they need to satisfy this sort of compatibility, known as absorption. And the reason one has all of these relations, we can think about this way more intuitively as posets. We can think of a lattice as a poset, so we can forget about the algebraic structure, only think about order theory structure. In universal algebra, one does not consider order theory, otherwise one has model theory. And we can think of a lattice like this as a poset with binary suprema and infima. And then the suprema precisely joins and infima meets, and we get a lattice above, so the equivalent. It's a really nice correspondence in a sense. You can read about it in the universal algebra book that was a footnote in the previous, or 2 slides ago, in the first chapter. It's a very brief chapter. I would recommend going through it. It's an important order theoretic notion, and it's just kind of a very nice theory one obtains. So we can require for lattices to be modular. It's just kind of technical condition that kind of is a weakened version of distributivity, because you might note that in the definition of a lattice, in general, it does not follow that infima distribute over suprema or vice versa. So one can characterize when they do. It's very simple. You have actually these two lattices, and you can say that something is distributive whenever neither of them embeds, or modular whenever only one of them doesn't embed. And well, modularity, this is this weakening of distributivity, which is this equality called modular identity. And the reason we care about modularity here is because when we have an algebraic structure, something usual to do is to study its lattice of congruences, lattice of substructures. In this case, you consider congruences. For ideal determined varieties, actually, the congruences correspond in bijection to ideals, and indeed, this becomes an isomorphism of lattices. And so a variety is called congruence modular whenever all of its algebraic structures have modular lattices of congruences. There's this condition, and it allows a very good definitions of commutators. So just something I wanted to mention, there's also these terms that can characterize congruence modularity, a little bit more complicated, but maybe it's nice to see that they exist. And what one can check is that any ideal determined variety is congruence modular. Actually, one can get an even stronger condition. One can prove that the lattices of congruences are what's known as argusion. Actually, I'm not sure if I'm pronouncing it right, but that's another condition of lattices. Well, but since they are congruence modular, we can talk about commutator theory within them, kind of compare it with the ideals. And we get some very nice theorems and relations between commutators and ideals, etc. If you're interested, you can again look for the ideals in the paper. I'm not going to go with just because it would be kind of, it would require me to introduce all of the commutator theory that comes with it. This is just what you can do because you have congruence modular varieties. So I kind of hope to give the landscape of why we can do commutator theory here, how it relates to the ideal determinantness. So that will be my whole talk. Thank you everybody for attending and listening. Here's some stuff you can read if you're interested about the stuff. For lattice theory, yes, you can read the first chapter of the universal algebra book I recommended, or you can have this whole book by Birkhoff, very important figure in universal algebra and lattice theory as well. For commutative theory, there's this very nice lecture notes in mathematics book. I think it's lecture notes in mathematics called Commutative Theory for Congruence Modular Varieties. It covers, it's pretty self-contained. I think it even gives you the background in universal algebra. It's not too long, it's 120 pages. You get some of the commutative theory from the first 40 pages already. So if you're interested, you can definitely read that as well. But that would be my whole talk. So yes, thank you for attending. Any questions? Yes? Yes, but there's an example where it's not equal. Well, actually, so if you look at the Boolean algebras example, I write s dot dot dot. That's because I couldn't fit it on. But actually here s is not equal to d, 0. You would have to pick as s, s of xy is not x and y, which is like one of the... So actually, in the Boolean algebras case, you have a funny situation because you can alternatively take two d's. You can take d0 on the left side, like x and not y, and d1 as not x and y. So saying that A or B0 is the same thing as saying A0 or B0. And then you Boolean algebra or lattice. Boolean algebras form lattices. And so in that case, we have two Ds, and then one of the Ds is the S. I'm not sure if you can always embed the S as one of the Ds. It's a good question. So yeah, I'm not sure. Yeah, sorry. So let me repeat the question for the recording. A person asked whether there's... okay, wait, I rushed ahead a little bit before hearing the whole question, but it seemed to me that the question was whether there are examples that the S is not the same thing as one of the DIs, which I don't know, but in many examples here it is the same, and in the last example it's not the same, but it can be picked as the same if you change the D0 and D1. So was that your question and did I answer it? I mean, at least partially. Yes, in this case, we cannot pick our D0 as S because we would not have the D0 axis S, 0 axis X, because we just have, what do we have? We have 0. So yes. Okay, thank you for the question. Any other questions? Okay, seems there are no other questions. You can always ask me a question later. So thank you for attending. Let me stop the recording.